exponents. So we have learned in the past class that we have learned addition, multiplication. We know that multiplication can be considered as a compact form of additions, right? For example, if I have numbers a plus a plus a, if I have n such numbers, I don't really have to write or expand all of those numbers. I can write this into a compact form by saying that it is actually equal to n multiply the number of a, right? So basically, it's the expansion of the addition to the multiplications. It's the compact way of writing addition into the form of multiplication. So intuitively, we can also thinking that is there a way that if I'm right now writing the multiplications of the same number a, for example, a times a times a times many a's, let's say also having n of number a that multiplied together. And yes, we do have a further compact form to rewrite this expression into a to the nth power, the power of n, or the nth power of a. Right, so this is simply a notation that just means that I have n such numbers are repeatedly multiplied together. So as a quick example, or let's simplify this first, you probably already heard about square, right? So square is actually a special case or a simplified case of power. So square is the product of the number and itself. Right? So then if I'm writing the product of a number a and itself, it's a multiply a, then go back to the compact form, it also can be written as a to the power of 2 or a squared. So this is the square, right? And as you can see, it is really just a simplified case where we let n equal to 2. So we'll go back to this general case or complicated case, but we'll now start with the simplified scenario with squares first. So then you may also already heard about perfect square. Right, so perfect square is the square of an integer. So for example, you probably already heard people saying that the number 9 is a perfect square. Why? Because it equals to 3 squared. For example, I would also say 144 is a perfect square because it equals 12 squared. Or in the opposite way, for every single integer, well, here we'll just narrow down to the positive integers. Every single integers, if you're taking the square, the number you got would be the perfect square. For example, 1 square is 1, 2 square is 4, 3 square is 9, 16, 25, and go on, right? So you have infinite many of the integers, you will have infinite many of the perfect squares. And your integers would be the continuous or consecutive numbers, but obviously your perfect square is not a consecutive series. Right? And also, before we're going into the further material, there's also a reminder just to repeat again what we have learned in the past about the order of calculation. So basically, you should compute power in front of multiplication, division, addition, subtraction. So simply power calculations in front of addition, subtraction, in front of multiplication, division, and then in front of addition, subtraction. Okay, so then let's see some examples about squares. So already see the definition of square or definition of power. And so far, all the examples or definitions are given in the form of a positive number. So what happens if I have a negative number, negative a, and I'm taking the square? So you will learn the conclusion very soon, but here let's start with step by step. So first of all, and you will see that how we derive the conclusion shortly. So first of all, square means the number multiplying itself, right? And then negative number equivalent to say that it's -1 multiply the positive part of the negative number, right? -1. And then remember by the the associative multiplication, I can further write this as -1 times a times -1 times another a, and then by the commutative of multiplication, I can shuffle the order of the 2 minus 1 and 2a's in a different order that I would like to write the 2 minus 1 first together and then the rest of 2a's by the end. And now you may remember that we have learned the plus minus signs in the multiplication, right? If you have negative and negative, you will end up with a positive number, plus sign. Right? If you have plus minus, it's minus. Minus plus, it's also minus. But minus minus, it's +1 or +1. And times here, a times a, you can directly refer it back to the original definition. So for any number a, it can be then written as a square. And because this is a positive sign, so then eventually it's just equal to a square. So which means minus a square equals a square. Right, then what happened to, or what if the power is not square anymore? Right, if it's to the third power, I can still expand this. Right, basically I'm just using the most basic definition of power. I'm just rewrite power into multiplications of the same number itself. And then here I don't have, well, you can still just trying to solve them all over again by using the associative and commutative of multiplication. But here there's another way, is to reduce your question based on a known conclusion. Basically, the first two items can be written as minus a square, right? And you have the third term as well. And then this, we already solved this just above here. So we already know that minus a square is equivalent to a square, right? Of course, you can solve it all over again, but we already know this conclusion. And then here, similarly, let's write it apart into -1 times a. And then again, this is commutative, so I can write the -1 in the front, and then have a square, have a here. And then it's just -1, right? So the sign is minus sign. Sorry, my bad. This is a. So then a square times a there. It means you have a times a times a. You have 3 a's. So by the definition, it goes to the a to the third power. Okay, so I can write more examples with fourth power, fifth power, sixth power, but here I can show you one conclusion right away. So basically here we have minus a squared equal to a squared. I have minus a cubed, power of 3. Power of 3 we sometimes call it cube. It's minus 3, minus a cubed. And then if I'm further writing to the fourth power, it will equal to a to the fourth power. And if I'm further writing with fifth power, it will be minus a to the fifth power. Right, so you probably see the pattern now. So minus a to the nth power equals either it equals a to the nth power without a minus sign if n is an even number, right? It true to the power of 2, the power of 4. If I'm writing further, it's also true for the power of 6. So which means as long as n is even number, or as long as your power is an even number of power, it cancels out your negative sign. Or in other words, this number always non-negative. Right, basically the even number of power always give you a non-negative results. And then if n is odd, then minus a to the power of n will equal to minus a to the power of n. Okay, next we're going to expand the power to a more complicated calculation and incorporate this together with multiplications, and we'll learn some interesting conclusions from there. So next, what happens if I have square of product? So for example, I'm no longer having just a square, but instead I have a times b squared. So first of all, if I'm just considering a times b as a new number, or as a new item, then it's still by the definition of power, it equals to this whole term multiplying itself. And then again, by using the associative and commutative rule of production, you will see that this can be written as a times b times a times b. If you reorder, still going to write all the steps one by one. So So you'll see clearly how it goes to, right? Then these two terms can be multiplied together first by the associative rule, right? So then it equals to a squared times b squared. Basically, a times b squared equals a squared times b squared. And what happened to the square of reciprocal? Again, first of all, let's examine the reciprocal of a, which is 1 over a squared. We can use the same way, start from the definition. We can expand the square into multiplications of 1 over a times 1 over a itself. And then it's 1 over a times 1 over a. Again, like you may already know something about fraction, but if it's okay if you don't know yet, basically by the fraction multiplication, it equals to 1 times a on the numerator, and then a times a on the denominator. So eventually it's going to be 1 over a square. So basically 1 over a taking the square equals to 1 over a square. And what if we go with a slightly more complicated case? Instead of 1 over a, if I have b over a, like both numerator and denominators are numbers other than 1, if I'm taking the square, it's just going to be the same process. I can expand this over b as b over a times b over a, and then you will see it will equal to b squared over a square. Right, so these are helpful formula or conclusions that you can use at a later time to, all can be derived from the most basic concept, but later on you can take advantage of just using the conclusion directly, and you will find that it will significantly save the time for solving more complicated questions. And lastly, I would like to, because up to here, everything looks intuitive. Most of the rules that we learned in multiplication or addition seems can be expand to power, but there do have cases that same or similar conclusion cannot be expanded from multiplication to power. So for example, the distribution, like remember in addition we have multiplication distributes over addition. For example, we know that a times b plus c equal to a times b plus a times c, right? But it's not true if you want to distribute power over addition. It is true if you want to distribute power over multiplication, right? So this is really similar to the distribution, right? You redistribute the power of 2 over the multiplication or over the division, which is fine. But if you have power that you want to distribute to addition or subtraction, it's not true. So first of all, by conclusion, I will prove it shortly, but by conclusion, it does not equal to a squared plus b squared. And how? We can simply verify this again by using the same way, start from the definition that a square or any power can be written into the form of multiplication. So a plus b squared is a plus b, multiply another a plus b, and then this is really just the multiplication redistribute over addition, right? So I have, if you remember how to do this calculation, it's equal to the first term multiplied together a squared plus the first with the second term ab, then plus the second term with the first term ba or ab, and then with the second term b plus, and then simplify this a little bit. It's a squared plus 2ab plus b squared. Right, now you can see the difference. As long as this ab doesn't equal to 0, then this expression is different from, well, it does not equal to a squared plus b squared. So this proves that you cannot distribute power over addition. Okay, so this conclusion is not only true for the plus sign, it's also true for the minus sign. I can leave this to you for your own practice. Eventually, if you're trying to prove a minus b squared, you will get the similar conclusion. Okay, now let's take a look at, or let's summarize the higher exponents. So already see a bunch of examples of squares, and some of them can be intuitively expanded to higher order of powers. So first of all, again, I go back to the definition. The nth power of a equivalent to the n a's multiplied together, so that if we reviewing the distribution of power over multiplication, like remember we just showed it, the conclusion to the squares, but if let's use the power of n instead of square, this conclusion is also true. You can still try to prove it by yourself, but it can be done just basically based on the same the most basic definition of the power, but here the conclusion is that a times b to the power of n is equivalent to a power of n multiply b to the power of n. And similarly, for reciprocal, 1 over a to the nth power is equal to 1 over a to the nth power. Similarly, instead of 1 over a, I have fraction form a over b. It equals to a to the nth power over b to the nth power. Right, so this is just a similar conclusion expanded from square to the nth power, and it's still true. But also a warning that a plus b, it's still not true when you expand to nth power. So basically, the power operation can never redistribute over addition, right? So it works fine. It redistributes fine over multiplication division, but this doesn't mean that you can redistribute over addition or subtraction. And then how about the associative exponential? Where exponentiation is associative. Is that true? So let's start with an example. So very simple example that, so what is associative of exponents? That means if I already have a exponent of 2 square, right? This is one number. And what happens if this 2 square, this number, further subject to the third power of the cube? So before we're learning any formula or conclusion, before we knowing any conclusion, we can again use the most basic definition, try to solve it. Right? So 2 square, first of all, 2 square is 2 times 2. And then if there's no further squares, this go back to the one of the conclusion over here that I have one more power operation that can be distributed or redistributed over multiplication. So it's 2 to the power of 3 times another 2 to the power of 3. Again, assuming that I'm not learning any further conclusion over here, this can still be written as I'm going to expand again the power into multiplications just based on the most basic definition, right? I can write this as 2 times 2 times 2 from the first notation, and then another 2 times 2 times 2 from the second term. And then this really just the associative rule of multiplication that I can just drop the brackets. It's just equivalent to 6 2's multiplied together. So I have 6 2's multiplied together. It again go back to the original definition. Then this can be written as 2 to the power of 6. Right? I have 6 of them. So now if you observe the question from beginning to the end, the answer, you probably find the pattern already is that if I have this form of power, right, a power over power, exponent over exponent, this is equivalent to the product. So 6 is equal to 2 times 3. Why is this a product? Because you have 2 terms here, and then you expand that 3 times, or you have 3 terms here, you expand that 2 times. So it's 3, either 3 times 2 or 2 times 3, doesn't matter, depends on how you're going to expand this number, but it's always equivalent to 6 items. Right, so that's how, so which means this is true. So this is associative and this can be written in the conclusion of power can be written as, if I have a the nth power and then further with m's power, so it can be any power n and m. This equivalent to a to the n time to the power of n times m. And this actually can be further written as equivalent to reshuffle the order of the 2 powers and taking the m's power first, then taking the n's power is still equivalent. So all these 3 terms are equivalent to each other. Now this can be further expand to product and quotient of powers. Right, here we review the power of power. Then how about product and quotient of power? So we actually already have the product of powers, right? Then what happened to the quotient of power? It's the same thing, right? So the quotient is equivalent to fraction it's a n over b n. Okay, now what happens if I have different powers, right? So this example or this simplified example just demonstrates the product over the same power. So now what if I have a to the nth power times a to the mth power, right? This time I have same number, or actually sometimes we call it base number, so same base, but different power. Then what happened? First of all, a to the nth power is equivalent to a times n of them. And then similarly, the second term can be expanded as also as a times a with m of them. And then altogether, how many a's altogether? This time it's not a production, right? This time it's not multiplying. This time it's the addition, right? The sum of the total counts of a, right? So how many in total have n plus m counts of a in total, right? So that means this, let me just copy this down to the bottom. So a to the nth power times a to the mth power is equivalent to a to the n plus mth power. Okay, so this is the product of powers. And then I will leave the detailed proof to you for practice, but similarly, the quotient of power, if I have a to the nth power divided by a to the mth power, it equals to a to the power of n minus m. Right, so for example, let's just see one quick example to see how to utilize this conclusion. So for example, if I have 3 to the power 3 squared times 3 to the 5th power. So let's see how to simplify this. We don't really have to solve it, but there's a way to simplify this by written into just one item is that you see that we have the same base. They're both base 3, but they have different power. And if this is a multiplication, then obviously I can write them or simplify them into one item with the same base, but this is a multiplication, so it's 2 plus 5 with the power of 2 plus 5, which is 7. Right, so this is just simply showing that if you have the same base with different power, they can be written together into one term. And this will going to be helpful when you need to simplify a complicated expression later. Okay, so lastly, let's see some examples to just practice what we have learned. So first of all, let's try to simplify the following expressions. First one, for example, if I have 2 to the 7th power multiplied 2 to the 8th power divided by 2 to the 3rd power. This one, remember what we just learned about the product of powers. Have an times an is an plus an divided by an is an minus n. Right, so basically just you to use the product of powers. So first of all, we examine that we have the same base, and base is number 2, base is 2. So then the first two terms equivalent to the power of 7 plus 8. And then I can either first just do the addition first and then consider the next division, or I can just keep going. I use the conclusion for the quotient of power. Then I further have the first item with the power of 7 plus 8. It's divided. Now it's divided. So divided means minus the same power. And then just simplify over grouping this number into 1. So it's 15 minus 3. So it's 2 to the 12th power. Okay, so next, let's see 2 to 6, then to the power of 4 divided by 2 to the power of 7. Right, it's a similar question that you first observe that they do have the same base. The base is 2, and then we'll just use the conclusion from the product and quotient of power. So 6 to 4. Now this is power over power. Remember that it's no longer plus, right? Power over power over is multiplication of the power, right? So it's power over power, so it's 2 to the power of 6 times 4 divided by 2 with the 7th power. So then this is 2, 6 times 4 minus 7, because this is just a quotient. So then this is 224 minus 7, so it's 2 to the 17th power. Okay, the next example, let's see what is 4 to the 6th power divided by 8 squared. Now this time they don't have the same base, so which means we need to check whether we can still apply these rules or there's no way to simplify. Sometimes there might not be necessarily to always be able to simplify any expression. It really depends on the actual numbers. Now go back to this question, even though they have differences. So the first item's base 4 and then this one's base 8, even though they're not the same, but you can easily see the relation between these two numbers because 8 is simply 2 times 4. So this gives us a hint to convert one of the number or maybe convert both numbers into the same base. So it's not only just 8 equal to 4 times 2, because if I have something 4 times 4, I can easily write as 4 squared, but 4 times 2 I can't really write into any further compact form. So this doesn't seem a good choice. So what would be a better choice? They are all the numbers, like both 4 and 8 are also correlated or connected to the number of 2. For example, 8 is 4 times 2, we just saw that, and 4 is 2 times 2, right? So the number of 8 is really just 2 to the 3rd power, right? And then, of course, 4, remember 4 is actually a perfect square of 2, which is 2 squared. So this means by applying any such rules, before applying any such rules, we can first convert the base number into the equivalent base. So then number 4 equivalent to 2 squared, right? So 4 is replaced by 2 squared, but 6 power should still stay here. Similarly, 8 can be replaced by 2 cubed, and then 8 square, and this square should also stay the same place. And then again, before we do any division here, we should taking care of the power operation first. And from this power operation, this is power over power, that we have a way to simplify this to be 2 to the power of 2 times 6. And then this is the power of 3 times 2. This can be simplified as 12 power of 12, and then this power of 6. Now I have the same base, I have power, I have division, then I can apply the quotient of power rule such that this will further equal to 2 to the power of 12 minus 6. So it's 2 to the 6th power. So this is how it can be simplified. Okay, next example. So assume that we already know that we know that 1 square plus 2 square plus 3 square onto 25 square is 5,525. Assume that we already know this conclusion. Now, what is, or to evaluate 2 square plus 4 square plus 6 square plus until 50 square. So what is this? So of course we want to use the conclusion or the condition that we already know and to find the similarity to compare with our problem and to see if there's any pattern or any relations. And to this question, obviously the relation or the pattern is that every number in the second expression is 2 times of the number that from the first expression, which is a known condition. So which means if I can find a way to simplify my second expression to be into a similar way to the known condition, then I might be able to solve this problem. So either you may already see the way to simplify that right away by factor out this common factor, but let's start with our observation first, because we, at least as the first step, we already know, or we can say that every number in our second expression is 2 times something, right? It's all even number. Even number can be written as 2 times another integer. So if I'm writing this as 2 times another integer, then this non-consequent series will become a consequent or consecutive sequence if we only see the second number. Right? In other words, it is consecutive even numbers. So if you factor out the common factor 2, the second number would be the same as the known condition. In other words, the consecutive integer numbers. So how do we then convert this back into the given condition? So first of all, we want to factor out common factor. So, but what is your factor here, right? Yes, like every number can be written as 2 times an integer, but you still have a square out there, right? So you need to get at least one more step to simplify or to rewrite this expression. So this is really just the power that redistributes on the over the product. So this is 2 square times 1 square plus again 2 square times 2 square plus 2 square times 3 square plus until 2 square times 25 square. And now you can see this 2 square, or you can just write it as number 4. So basically this is your common factor. This is the product of two numbers. There's no other notations, so which means you can factor this out. Basically this is just the reverse way of redistribution, or redistributes multiplication over addition, right? So basically this A is a sort of common factor which can be factored out. So here my 2 square is the number that I factored out, which means what left at the second term will be 1 square plus 2 square plus 3 square until 25 square brackets. Okay, so then this is our known condition, right? So we already saw the sort of relation or pattern, and then we actually reduced the question back to the known condition that given in the beginning. So then this whole expression can be substituted or can be plugged in with the known conclusion, which we already know that the sum equals to 50, 55, 25. And then it's really just 2 squares 4 times, it's really just arithmetic of finding the product of the two numbers. Right, so this is one example. And let's see one last example for this lesson. So if I have a number 10 to the 93rd power, subtract 93. If this is a number, what is the sum of digits? Right, so if this can be expressed as one single number, basically if this can be simplified as one single number, what is the sum of all its digits? So basically we just want to find the digits of this number, or at least the pattern of its digits. So this is really just a subtraction of two numbers. If you don't see the pattern, I don't see the pattern right away, so let's try to write this apart into a couple more steps. So first of all, the first number, 10 to the nth power, for example, 10 square is 100, right? 10 cube is 1000. So 10 to the nth power, it's always start with number of 1, and you have n zeros after 1, right? So this is the pattern. So for example, the first number can be also written as a number start with 1 and followed with 93 zeros. And what's the result of this number minus another 93? Let's check or let's start from the easier case. If I have 10 squared minus 93, this is 100 minus 93, this is 7, right? If I have 10 cubed, this is 1000 minus 93, that is 907. And if I have fourth power of 10, I have 10,000 minus 93, I have 9907. And if I further expand to fifth power, skip the middle term, but it will be 99907. Now you probably find the pattern. Basically, because I'm subtracting 93, so the 1 digit and 10 digit, the last 2 digits will always be 07 or 07. And then start from the 100 digits until the very first digits, it will always be nines. Now the question is really just how many nines do I have in front of 07? And you see the pattern. If the power is 3, I have 1 9. If the power of 4, I have 2 nines. If the power of 5, I have 3 nines. Basically, starting from 10 cubed, the one more digit I have power of 10 give you one more digit of 9. So, right, if this goes to 10 to the power of 93, I will have 93 minus 2 nines, right? This is 5, this is 3, 4, this is 2, 3, this one's always minus 2. This is the pattern. So having 93 minus 2 nines. So I already know the number, like even though I don't know the exact value of the number, but I already know the pattern of this number. So, because we only need to know the sum of its digits, basically, I just need to know the sums. So I have 91 nines. So the sum of all the digits for nines, I have 91 of them. And I have a 0, and I have a 7. And that's it. So the sum will be 826.